Morning, everyone. Today, inshallah, I probably did not share the screen. So let me share it. All right, much better. All right, so today we're going to talk about a method of, again, determining the stability of a system. But here is going to be more detailed, and actually you'll get more information about the system itself. So last week or 2 weeks ago, 2 lectures ago, we talked about Ruth Horowitz, about the stability criterion, and determine the value of K that will make the system stable, or determine if the system is stable. Now, let's have this scenario. So we always have our input, X of S. We have a certain block, G of S, and we have the output Y of S. So in this case, we have an open loop system. There is no loop. And whether the system is stable or not, we have no control of it. So the solution was to provide it with a certain feedback. So we'll have a system like this. So for now, I will, okay, yeah, we have a summer. I forgot to add the adder. Eraser. So I'll have the adder indicating feedback. Adder usually is like this. So we have negative, positive. Okay, so I'll draw a certain block here. I'll keep it blank for now. And we have the system. G of S, it's the same system itself. And to make things easier, I will not provide it a feedback block. I'll keep it a unity feedback. And then to have a control over the system, I'll just multiply it with a constant K. Now, the whole thing about the root locus is determine the behavior of the system for different values of K. So first, you start by locating the poles in the S-plane. So let's assume that you have poles here and there. And then if you vary K, that's the initial case when K is 0. But now you change K to 10. And then realize that this pole has moved to this side. So it's here. And this pole moved to this side. Then make K equal 10 and 20, etc., etc. So you start K from 0 to infinity. And of course, we'll not draw to infinity, but we'll draw something kind of describes the system response or behavior for different values of K. So what is the root locus? So it is like the locus or the graphical representation of the closed loop pose as a specific parameter, usually for the certain constant gain when it's varied from 0 to infinity. Now, why do we need it? It's more analytical than the Ruth Horowitz. So we analyze the transient response qualitatively and the effect varying gain upon percent overshoot, settling time, and peak time. Actually, those terms are very common in control systems, yet we do not cover them in the course. Hopefully, inshallah, this course will be gone under revision, and we'll introduce these concepts into the course. So we can also use the root locus to check the stability of the system. Again, pretty much like the Ruth Horowitz, but Ruth Horowitz tells you stable, not stable, but it will not show an exact behavior of the system. So that's a typical scenario we usually have. We have a feed forward or forward transfer function. We have a feedback. This is the overall transfer function when we apply the feedback block diagram reduction. So we use the root locus to analyze the feedback control system. K in the feedback system is called the gain. Gain is used to vary the system in order to get a different output response. Now, this is a general form for a feedback closed loop system. This is the one that we will be focusing on. So for easiness, usually we have this one as a constant or 1 or whatever, and this one just K. Actually, when this example simplifies it, it will just say K1 times K2, just a constant K. So when you have a system like this, and it asks you to determine the transfer function for the system. So you have a G, which is 1 over S plus 10. times k. They are the series over 1 plus the same thing. Again, remember when you have a negative sign, so that's a plus k over s plus 10. So the simplification will become k over s plus 10 plus k, or simply k over s squared plus 10s plus k, which is the same exact expression here. So just avoid like just to simplify from the beginning, k1 and k2, they are a constant k. So what will be the dynamics of the system for a varying values of k? So here is the same example now. Now initially when there is no k, when k is 0, the poles were at, so this one, s squared plus 10s equals 0. So take s as a common factor, s plus 10. So initially I have my poles. Okay, so I have as 0 and negative 10. Now, if the value of k equals 5, so try in your calculator, s squared plus 10s plus 5. That should be easy because we want to confirm these values. So I will assume that we will be getting these values. All right, so it says that when the value of k changes from 0 to 5, this pole that was initially located at 0 has moved to this location. And this pole here has moved to this location. Now increase it to 20. Let's try the 20. Yeah. So s squared plus 10s plus 20. Exactly. So I'm assuming it's going to be the same. So we will have that's a negative 7.24 and that's a negative 2.76. Now the case when they are both equal, when this value is 25, so it's going to be s plus 5 squared. So we have 2 roots at the same location. So that's a negative 5. Now notice once they, I will not say collide, but once these poles are the same value, when you increase the value of k, now we'll go into the imaginary space. Now we have sigma plus j omega. In fact, the S-plane usually is like this. The real part is sigma and the imaginary part is j omega. That's another way of looking at the S-plane. All right, so when we plot or draw this, we kind of see a behavior of the system. Like the first pole will be going to this direction until it hits -5, and then it will go to this on top. That's the first pole. Okay, that's a straight line. Let's assume it's a straight line. And notice like it keeps going up vertically. The imaginary part is always negative, and the real part is always -5. So it's like a column on top. Similar thing for the other pole that started as 0. It keeps going there. Again, that's the point of intersection or collision, and it goes all the way down. And this is what we call the root locus method. Now, you realize that doing this is time consuming. There's no time to like find for all values of k. So that's why we need like to sketch the root locus. This is the like what we call drawing. Why? Drawing point by point, and then you just match the dots. Now we'll see the form or the procedure for sketching the root locus. So this is the drawing the root locus, as I mentioned, point by point, then connect them with a certain line. All right, so the process of drawing is time consuming, of course. Then we'll practice the sketching. And there are several rules when we sketch the root locus. So how to sketch it? There are 7 rules. And you don't have to do them in order. Like you can start with a certain point, then you do the other point, etc., etc. So it's not something that, oh, I need to go 1, 2, 3 in a certain order. All right, so the rules are: step 1, prepare the root locus sketch. Make the function in this form: 1 plus kps, and p is the characteristic equation. So write the characteristic equation so that the parameter of interest k appears as a multiplier. Now substitute this p of s, the characteristic equation, into this form, the form of zeros over poles factorized. So let's assume that I have a square plus or just keep it as s plus 5 over s square plus 5s plus 6. So make it as s plus 5, s plus 3, s plus 2. And you know the symbol? Okay, you know the symbol, right? Summation. This one we call it upper pi or whatever. It's a pi, but this is a product. So this one we have xi. It means that it's x1 plus x2 plus x3. Here for xi, it means that x1 times x2 times x3. So just a product. So that's why it's saying that make the transfer function as a form of products of poles and zeros, or the factorizations. Now locate the open loop poles and zeros of PFS. So you start with like there is no k. And as the previous example, locate the open loop poles and zeros. Okay, let's assume there are zeros somewhere here and there, whatever. And that's plain. Now determine the number of separate loci. Separate loci stands for SL. All right, so we'll talk about the separate loci in a minute. So that's X for poles, zeros for that's an O for zeros. So the locus begins at the pole and it's a zero. That's one rule. So the locus means that's the line. Like in the previous example, that's the locus. So one of the rules, the locus should start from a pole and should end at a zero. Should end at a zero. Now, what will be the case if there are no zeros? It will go to the infinity. Like this in this case, there are no zeros. So it keeps going all the way up to infinity for both sides. All right, so that's one key point here. Keep it in mind. It will stop at the zero. So let's assume that there is a pole here. Let's assume there is no zero here. This pole will go to this side. It will stop there. This pole, there is no zero matching it. It probably will go to infinity. All right. So the root loci are symmetrical with respect to the horizontal real axis. Basically because we have conjugates. So it has to be symmetrical over the x-axis. Like in this case, like over this axis, they are mirror images. They are the same. If you have something like this, you will have something like this. If you have something like this, you will have something like this. They are just mirror images over the x-axis. Now locate the segment of the real axis that are root loci, something like this. So locus lies on the left of an odd number of poles and zeros. So usually the loci or the locus lies to the left of an odd number of poles and zero. Yeah, I never see this one in action actually. We'll see it like if we can make a conclusion out of it. All right. Now, once we do drawing, so let's have some example here. And there is this scenario, you have 3 poles, no zeros. At -1, -2, -3. Now there are no zeros. So all of these poles will go to infinity. Now, this one here will be going all the way to this side. That's like from the example, we'll see that it's going to this side. Now these poles will hit each other. There will be something called collision. Now this point here, we will call it sigma A. And sigma A is the point of intersection of the asymptotes. You know what asymptotes? You've done that in calculus and math. Asymptotes. Asymptotes is like the tangent line of a certain curve. For example, let's assume that I have x equal y squared, for example. Something like this. All right, so this one is the asymptote. Okay, it's tangent for this line, something like this. In Arabic, we call it al-mamas. So it touches the curve at a certain line. Now here sigma is the point of asymptotes. That's the intersection of asymptotes. Asymptotes will be something like this. For example, in that example, we'll see that these are the asymptotes. So sigma A is calculated as the summation of the negative of poles minus the summation of negative of zeros over the number of poles minus the number of zeros. So n here is the number of poles. I think it was mentioned here. So n is the number of finite poles or the poles, and p and m is the number of zeros. So that's the formula for m. And again, see here, like I did not rely on the previous work. I can start by this. Like find my poles, find my zeros. I can automatically locate sigma A. Now, what will be the direction of poles? The direction of poles is given by this formula. Oops. 2k plus 1 over n minus m. So I have the n minus m. Now 2k plus 1, k is a constant, is a factor. If I have three poles, not three, it's the difference between poles and zeros. If n minus m is 3, so I have 3 points from 0 to 2, 0, 1, 2. If I have n equal 5, for example, I have 5 poles, and I have 1, 0. So n minus m equal 4. So the values of k should take 0, 1, 2, 3. 4 values. So you have to calculate 4 times. These are the directions or the angles of the asymptotes. So this is the angles. These are the angles of the asymptotes. That's phi A. It's going to be always positive. If it's 90, 180, 270, it's always a positive angle. And you know, with x-axis, this is how you do the angles, like this. So this is a 270. This is 315, 300. Yeah, something like that. So, you know, the whole circle is 360 degrees. All right, so this is the direction or the angle of the asymptotes. Now, why do we need the asymptotes? Because, again, asymptotes are imaginary axes. So it's not part of the sketch. So that's why it's better to have them in dashed lines. Asymptotes. In some occasion, the line itself, the loci, the pole movement, is exactly on the asymptote. For example, let's assume that we have an asymptote like this, and then I will have a loci like this. It's fine. Exactly on the asymptote. Most important part, you can never have an asymptote and the line intersecting like that. Again, asymptote is a mamas, is the line, is the tangent line. So you cannot have the asymptote crossing the line. All right, so determine the point at which the locus crosses the imaginary axis. So basically, determine the values of k to check if the system is stable. And we pick the case when the system is what? Marginally stable, because that's what the imaginary axis, like you have it something like here. And in this case, there always have to be conjugates. I know it's a lot, but not once we put everything in action, solve an example, you will see like it's kind of straightforward. It's a bit easy. Actually, there is another method in the slides. We will try to do both. Now determine the breakaway point on the real axis. Now, what is the breakaway point? So again, we mentioned that these poles, for some reason, they will intersect, like in this example. Here. That's what we call a breakaway point. Breakaway point or break-in point. It depends on the movement of pole. So the breakaway point is the point where poles collide. And it's not the same as the sigma A, that's the point of intersection of asymptotes. They are two different things. Now, how to determine this point? So basically, you look at the transfer function, you want to maximize it. So make it like this, K equal negative P of K, P of S, your transfer function, and make sure you have the negative sign. Just take the derivative with respect to S and equal to 0. And you might get 2 points. You only need one. How you want to determine that one? From your imagination. Notice here that I constructed something. I may have a breakaway point here and another breakaway point here. Which one you will pick? This one. Because my intersection is this point. So I will assume that my sketch is like this. All right, determine the breakaway point. So set K equal P of S or negative P of S, and determine the roots of dP over ds. Determine the breakaway point, determine the angle of Locus departure from complex poles and the angle of Locus arrival at the complex zeros using the phase criterion. This is the phase criterion. I never use this formula, but it's still there. And then just complete the sketch. Basically, you have all the components, and yeah, your drawing doesn't have to be the most beautiful drawing. Just to me, I will look for more into the math part, and something like this is acceptable to me. Like even when I draw it, it's not that good looking figure. I will look more into the numbers, then I will give the sketch another look. All right, so we have the scenario here. So sketch the root locus for the following system. So now you see, you don't have to do the feedback because it's going to be the same thing. Try the open loop. We'll find what the poles. So I'll make an initial sketch here. How many poles I have? I have at 0, at -1, at -2. All right. Now, can we find the value of sigma A? Was a summation of negative pi minus summation of negative zi over n minus m. How much is n? 3. How much is m? 0. And p of I, so I have p1, p2, p3. I have a 0, I have 1, I have 2. So I will have -0. لا البيس, but then when I substitute I will put the negative. صح. Negative. Okay, -1. Okay. P0 equals 0, P1 equal 1, P2 equal 2. No, it's not the poles. It's S plus PI, right? You go back here. It's S plus PI. Okay, so it's S plus 1. In the formula, I will substitute -1. Okay, so that's a good point. You pointed that out. So we know that the poles is, this is not the pole, that's the negative of the pole. Because S plus P. What will be the pole? Negative P. So in fact, you go back here. So P1 is 0, 1, 2, then we substitute them. Or you just summation of poles minus summation of zeros to avoid confusion with the signs. Sum of poles minus sum of zeros over n minus n. All right, so I have 0 plus -1 plus -2 over 3. So I get a -1. So here, okay, -1, -2 over 3, n minus m. Yeah, that's a -1. So it is here. Okay, so I have 3 poles, no zeros. So let's see how it started here. So the Lucy and the real axis are to the left of the odd number of real plane. The red lines and the S-plane are parts of real axis where the root locus exists. So my line should be here. Lines. And notice that these 2 lines will intersect at some point. This is not the drawing. This is just an initial sketch that this is my imagination. The poles will intersect. This one will go to negative infinity. Why there will be intersection here? There is no 0. If there is a 0, yeah, from pole to 0, it will stop. But from pole to pole, it will not stop. But it's just saying that my line is located here, or my lines are located here. All right. So sigma intersection of point of asymptotes with the real axis. So that's a -1. So go back here. Here's my sigma. Now, what will be sigma A? Now, what will be the value of phi A? Remember, it's 2k plus 1 over n minus m times 180 degrees. That was the formula. We can confirm 2k plus 1 n minus m 180 degrees. So how to apply it? So what will be the values of k? So I have n minus m equal to, so 0, 1, 2. صح minus 1. n minus m minus 1 from 0 to 2. Yeah, I did it here right, but I put it like n minus m should be 3, minus 1 should be 2. Okay, so at k equals 0, that's the first asymptote. So what will be the angle? 1 over 3 times 180, so that's 60. At k equal 1, what will I get? 3 over 3. 3 over 3, 1, yeah. So that's 180. At k equal 2, 5 over 3, 300. Right. Again, asymptotes are imaginary lines. So that's at 60. That's at 180. And this is a 300. 300 is 60 down. So this is the angle 60. That's what I meant by 60 down. All right, so I have these components. Now we agreed like these 2 poles will intersect with each other. Like there is some movement. This one will be going this way, and this point will be going this way. And this one has to go to negative infinity. And here's the thing. So I have 3 poles. I have 3 asymptotes. Each pole movement, the Lucy, will be associated with 1 asymptote. Like this pole would be associated with this asymptote. This asymptote associated with this pole. This asymptote could be associated with this pole. This one here automatically is associated with this asymptote. So this pole I know will be going this way. So that's actually the first line of interest. That's the movement of the -2. All right, what other components I need? Breakaway point. The point where they will intersect. Like I know that this pole will be moving to the left and this pole will be moving to the right. There will be intersection. Actually, there is an easier way to find it. It just you look. This is my characteristic equation. Like even when you do the feedback thing, you'll get that same thing in the denominator, plus k. So you just make k equal negative that thing. S plus 1, S plus 2. So let's expand this. K equals negative S cube. So I have 2s3s minus 3s squared minus 2s. Check, confirm. So s plus 1, s plus 2 is going to be s squared plus 3s plus 2. Multiply everything by s. You get the same thing? All right, so dk over ds. Negative 3s squared minus 6s minus 2. And this one you give it a 0. So what will be the values of s that will satisfy this formula? So I have s equal negative. Give me 3 decimal points. 422. So that's s1, s2 equal negative 1.57. 8. All right, so let's look at the location of the point. I say that it's somewhere here between the 0 and negative 1. Now let's look at these values. Which one satisfy that condition? The negative 0.4. So I'll exclude this. So this is my negative 0.422. All right, so we have technically solved it. We said that this asymptote is already going there. And this one will be moving here and going like this, asymptote. And this one will be moving there and have this asymptote. Now, someone might ask, why did you decide this will be going there and there, or this? It doesn't matter. Because it's going to be this, it's symmetrical over the y-axis. So it's not an assumption. I know that both of them will look like that because symmetrical over the x-axis. Now, what will be left is to determine this point. Intersection with the imaginary axis using stability, Routh-Hurwitz. So this one, when you do the math, so let's try now to find the feedback. So it will be G K over S plus 1, S plus 2 over 1 plus S plus 1, S plus 2. I just want to confirm. I don't want to. So put this one down. You will get K over. K over that thing. I'm K. So, okay, so you'll get S plus 1, S plus 2 plus K. So this one will be again S squared plus S cube, sorry, plus 3S squared plus 2S plus K. Huh? Okay, I don't have the proper space for it. Let me rewrite it. S squared cube, sorry, plus 3S squared plus 2S plus K. So how to find the root locus for this one? Sorry, the Routh-Hurwitz. I will have 1, 2, 3, K. S cube square as suppose 0 صح. All right, so it will be the value here going to be 6 minus k by 3, and this one zeros because I have the columns there zeros. Now what will be the value here? Okay. All right, to have the system stable, what is my condition? So yeah, so I'll have 6 minus k over 3 is larger than 0, so what will be the value of k? Greater than 6. Less than 6. Less than 6. And this one I have it 0. So the values of k so the values of k 0, k 6. All right, so why do I do this? Because I want to find the intersection with the x or the y-axis. Now, what is the meaning of 0 less than k and k less than 6? So again, I want to make the system marginally stable because that's when the intersection with the y-axis. So when you have this, when you have the value of k 0, no, marginally stable. If it's less, not stable. Larger, a bit stable, but at 0 exactly, marginally stable. Same thing at 6. Larger than 6, not stable. Now we need to substitute, and then what? Another thing. Where راح الماركر? What is this axis? The j omega axis. And this one is the sigma axis. The sigma, not sigma a, that's the sigma. That's why I call it the sigma a to differentiate it from the sigma. So we found the values of k to be 0 and 6. Now let's try the case with 0. And the transfer function itself.
Without before move
this one here. After doing everything, yeah. So basically, I will have the same function itself. But again, we have s, but I have j omega. How to associate between them? My axis here is j omega, and I have my transfer function in terms of s. No. S equal j omega. No, let's try to. Okay, let me take a screenshot of this. I don't want to lose my plot. You can screen. Okay. Discard. Even though it's solved, I don't want to lose. حلول بس انه لا see that I don't want to go over the slide and tell you this. It's better to go over it, learn from mistakes, but we don't see the flourish kind of solution. Oh, everything is easy. We've seen some challenges here, like the easiest one, the summation negative pi minus summation negative zi. We thought that we put the negative of the poles. No, in fact it was actually the poles. Okay, hopefully it did print the screen. Control V. Control V, perfect. So I have my slide here. And we said, so we'll do the case. So I have s cube plus 3s squared plus s 2s. And we said we'll substitute s by j omega. So I will have here j omega cube plus 3j omega squared plus 2j omega. J omega cube, how much? Negative j omega cube. Plus. Okay, so it's going to be minus 3. Then you j omega square equal j square omega square. نعرف إنه j times j equal negative 1. So it's going to be negative omega square. Same thing here. J omega cube. On j cube omega cube. So omega cube will remain there. J times j times j. Negative 1 times j, so that's a negative j, 3 omega small plus 2j omega. All right. So we have imaginary parts and we have a real part. So that's the case when k equals 0. Now, when do you have the point located here? That's imaginary part. What about the real part? Flash.
Because it's right on that.
Right at the center of the axis. فالreal part اللي هو x axis it will be 0.
So we said it equal 0.
So yeah, omega equals 0. However, in this case, what will be the real part in this case? The imaginary part. It did not serve us well. It's 0 also. At omega at k equals 0, we got omega equals 0. The target is to find omega in this question. Now let's try the other case. اللي هي k what? 6. So it was plus 6. Just it's the same thing, plus 6. Now my real part, so at k equals 6, what will I get? What will be the value of omega?
طبعا نسوي الفكره كده طبعا.
Okay, الترانسفير فانكشن شو كان؟ s cube plus k. جربنا الكيس لما كانت k equals 0. We tried it with the k equals 0. We reached we reached a dead end. We did not get any information. Huh?
هاي كل كمان يكون 0. لا بس
simplify. Real part لحال, imaginary part لحال. Look for the real part, make it 0. لأنه هي على الأكسس. So, okay, it's not that equal 10, 0, whatever. لا. I have this transfer function. Substitute instead of s, I have j omega. Okay, so once I did the substitution, I will look for the real part, make it equal 0.
اوميجا.
لا مش اوميجا, الريال بارت. لأن عندنا اوميجا هون, عندنا اوميجا هون, عندنا اوميجا هون. الريال part that does not have j. هاي أول case. Negative 3 omega square equal to 0, so omega equals 0. But however, it did not serve us well. But we reached nothing. I want some like other values for omega. Now let's try with k equals 6. Same formula. J omega cube plus 3j omega square plus 2j omega plus 6. Simplify. Negative j omega cube, negative 3 omega square plus 2j omega plus 6. When the real part. Okay, so negative 3 omega square plus 6 equal 0. هذا الريال بارت. فأوميجا شو تساوي؟ plus minus square root of 2. اوكي؟ خلاص ففي عندنا هون هاي راح تكون على j square root of 2. remember انه هذا imaginary axis فالj موجودة. negative j square root of 2. What is your method?
يطلع غير الجواب صح؟
أول واحدة حطيت سيكون كي إيكوال 0 يطلع لي اس كلها ريل نمبر فأنا خلاص ما بغيرها.
اوكي
الثانية حطيتها إيكوال 6 يطلع لي واحد ريل نمبر واثنين imaginary. هو 1.1 j minus 1.4 j.
والريال 1 اوكي 3 من جت 3
يعني ما في ضايع ما بدأ نحولها للجي دبليو.
بالسلايدات they do with the JW. Yeah, you can do that I think with the S.
أصلا اس إيكوال j.
You will get the J automatically مع الانسر. True, yeah, true. You can do that. ها؟
شو نعمل؟
Both cases عادي I'm fine. I'm flexible.
تصل بالمثل تبعها بين اس
Now basically you have this for this whole formula. A K كانت 6. Just find the roots. S cube plus 3 S squared plus 2 S plus 6 شو الروتس بيطلعوا؟ You must have 3 roots a cubic function.
طلع نكتب 3 1.41 جي minus 1.41
تعرف انه هي نفس سكوير روت اوف 2 صح؟
1.41
هي نفسها.
ولا نكتب 3 اليوم.
Just ignore it لان احنا بنطلع على imaginary axis. All right, so let's see. Oh, that's it. So I have all the key components of that's it. That we did the sketch already with the values and everything. So let's see the slides. Okay, so started with the poles, assuming there is no K at all. We said that the lines should be something like this. Pole will be poles will be colliding with each other and this pole will be moving toward the infinity. Find the value of sigma. We find that's the intersection of the asymptotes and these are the directions of the asymptotes. So it was this one 60, 360 and 180. Oh, sorry, 300 and 180. And again, the asymptotes is the imaginary line, so we put it in dashed line. كيف عملتوها dashed ولا لا؟ أيوة dashed line. Okay, then the breakaway point. How to find it? We transfer the function, then we'll find dk over ds. And we'll find the roots for this function. We have two values. We pick the value that is between these 2 points because we have an idea that the point should be between 0 and -1. So it was this point. Then we found it. That's the sketch. Now we are only left to find the values of the intersection with the imaginary axis. Here they did the method I told you about. Change to j omega, take the real part, imaginary part. You can use the same method Aisha mentioned. And the value, see here, you will have omega plus minus square root of 2 when you have k equals 6 and 0 when you have k equals 0. Okay, من الروث هورويتز. We found the values from 0 to k.
بس كانوا ما كتبوا
هون ما استثنى الروث هورويتز لانه هي اخذ الكي عمل الجنرال كيس k minus 3 omega square j 2 omega minus omega square. I think how they did it, which yields equating both real and imaginary parts to this equation to 0. Okay, so he made it to 0. So how to make this value 0 at omega? When k equals 6, this value will become interesting. Yeah, how did he determine this value? So this one's straightforward, but this one I think from trial and error. That's my assumption because. But why did he do the assumption? لا متى عمل 0 لل 6 from روث هولويتز حالتنا صار انهم ما عملوا روث هولويتز صح؟ بس انه why did he assume that k equals 6? That's from the Ruth Horowitz. We did it. The slides they did not do the Ruth Horowitz. So where did he come up with these values?
لو عندك نص قديمة بس فاضية شو؟
لا هاي أول مرة بعمل ريكوردينج لها.
الحل اللي كان على السلايدات شوي.
I think it's better to do the Ruth Horowitz, get these values and do the solution to be on the safe side. Sometimes these slides, they assume that there are things that are done. So we have the recording there. We did the root Hurwitz. So we got the values of 0 and 6. And that's I think that's the better way to do it. That's the standard way to do it. Do the root Hurwitz, get these values. All right, and that's it. It did the sketches. That's k equals 6. That's not the intersection. So here we have j at j omega j square root of 2. Okay, so that's it. That's the sketch. All right, how to do it in MATLAB? Just simple line. So you have clear all, S equals transfer function of S, then write the form in the fractional and just type R locus of the system, root locus, and it will do it for you. All right. So that's a different example here, which was solved. I put that also on the website and the on model page. It's the same example solved. Same thing. So started with the sigma A, alpha A. I know the number of zeros, number of poles are already known. Summation of poles, summation of zeros. So intersections are -2. The directions same. Take the derivative for this whole thing. So the two roots, exclude this one. We only consider this one. Okay. Determine. Okay, he did the root locus here again. The root Hurwitz, sorry. So that's the standard way to do it. Find the root Hurwitz. Determine the values of k where the system is marginally stable, and substitute in the transfer function you are given. Find the values of omega. In this case, example 10. And in this case, for k larger than 60, system will be unstable. And that's it. And this is how you do it in MATLAB, the same example. So I suggest you try this and see if you will get the answer. By the way, in the exam, لا لمت لا.
انت عندك روت هوبس.
ايوه حكيت امبارح بالايميل. قرأت الايميل؟ بعت ايميل. بعت ايميل صح؟ This will be given for you. So you don't have to worry about memorizing formulas and put a lot of effort on that. Is it clear, the root locus? By the way, this is the hardest topic in the course. Really, this is the hardest topic in the course. All others are straightforward. جميل.
بعد البلوجر.
signal flow graph. هذا last lecture. Okay, so stop sharing. Record and stop the recording. Inshallah, the recording